title of my talk is the dynamics of the asymmetric wedge billiard in a constant gravitational field. And this is just a brief overview of what I'm going to talk about, outline of the talk. And yeah, it's not working. Sorry, just okay. Excellent. Okay, so first question, why billiards? Why are we interested in studying these systems? And I thought I'd give a simple example of two masses on a smooth horizontal surface. On the left-hand side, you have a wall, and on the right-hand side, the masses go for infinity. That's illustrated in the picture on the left. The picture in the middle is what they call the configuration space. So this is an illustration of both positions of the two masses simultaneously. And the picture on the right, it just illustrates sort of what's going to happen in the configuration space as these two masses move and collide. So a collision would be with the x2 axis or with x2 is equal to x1. I realized this morning that I made a slight typographical mistake with these images. And what's illustrated in this configuration space is actually for my x1 and x2 swapped around. So you either swap the position vectors around, or you can reflect the configuration space around x1 and x2. In this system, we achieve a very interesting result. If the ratio of the two masses is some multiple of 1, then the number of collisions between the two masses and between the M1 and the wall is finite and equal to n plus 1 digit number, which you can see there in the second equation. And this n plus 1 digit number coincides with the first n digits of pi. Right? There's a YouTuber, three brown, one blue, that does a video of this, explains it all quite nicely. Thank you. But why do we swap from this system of two masses to this configuration space? Well, it's essentially, if we look at the configuration space, it's equivalent to a single particle moving around on a two-dimensional plane colliding with walls. And we can always say that it's easier to study one particle than it is to study two particles. And that's what leads us to these type systems. Billiard systems are also beautiful and simple dynamical systems, but with the same complexities that you would find in general Hamiltonian systems. In the limiting case, it's usually geodesic flow. It's a limiting case of geodesic flow. And in billiard theory as a whole, there's a lot of theorems that illustrate concepts from topology, geometry, and ergodic theory. Right, so quickly, a brief history. Billiard systems essentially originated in the kinetic theory of gases in the 1800s, which was studied by Bernoulli, Maxwell, and Boltzmann. Hadamard and Artin also studied these systems, although they didn't call them billiard systems. The first true reference to mathematical billiards is by Birkhoff in 1927, when he used convex billiards to prove a theorem related to the three-body problem. It's now known as the Poincare-Workov fixed point theorem. Then authors continued studying convex systems and trying to find results about it. But there was a simple work in 1970 by Sinai, who introduced a new class of systems called dispersing billiards, also as a model for Lorentz gas. And I'll illustrate this a bit later when we look at some examples. And this class of billiards was shown to be chaotic in the sense of ergodicity and mixing, which was quite a novel result. And this paper by Sinai actually renewed the interest in mathematical billiards, and it's still an ongoing open research area. And it also opened the doors to consider other types of systems in the quantum or relativistic regime, if the particle is either very small or moving very fast. Billiards where they're moving within potential fields, like a gravitational field or a magnetic field. There is also this concept of open billiards, where your billiard table has a hole in it, or the boundary has a hole in it, and then trying to see how long it takes the billiard particle to escape. And also outer billiards, where, and this will become clear in my next slide, usually have some boundary, and from my first example, the billiard was moving inside the boundary. Outer billiards, you've got it moving outside. So there's some research being done in that as well. Right, so let's formalize what a mathematical billiard is, because billiards are considered playgrounds for mathematicians. This is actually the title of an article which I've put there at the bottom of the slide. And a mathematical billiard system consists of a billiard ball, usually represented by a point particle or a point mass. And it's generally assumed to move freely and with constant speed. There are some modifications, like I said, when it's like a magnetic potential or in a gravitational field. You also have a billiard table, which is a closed, bounded region in R2, generally. And also some collision rule. Generally, this is assumed to be elastic and obey the law of reflection, so that your angle of incidence is equal to the angle of reflection. But again, there are some billiard systems where authors change this rule, where they might say it's a dissipative billiard ball, so that the collisions are not elastic, and then they try and see what they obtain. But the reflection law gives the last equation there on the slide, which just relates the momentum after collision to the momentum before the collision. And I also want to just talk about the walls of the billiard table itself. Now, usually the wall is the boundary of our region, and we tend to fix an orientation so that the region lies to the left of a wall. And using that, we can, using some terminology from differential geometry, distinguish three kinds of wall. One where the wall is flat, usually that would be represented by a straight line. And then you have a focusing wall and also a dispersing wall. The only note is that on the right-hand side of this slide, where I gave it in terms of the curvature, in the billiard literature, the sign convention between focusing and dispersing is opposite to what you would usually find in differential geometry. But this is just to sort of, I will show examples of this in a bit, just to be able to talk about what is a focusing wall, what is a dispersing wall, and so on and so forth. All right, let's illustrate some of the classical examples. The first one is the circle billiard, where your region is a circle, as the name says. And you can actually derive the two collision equations, which I've listed there on the slide. What is interesting about the dynamics in this example is that it's completely determined by that angle psi, which is the angle between the tangent at the collision point and the trajectory of the billiard. If that angle psi is rational, then your orbits are completely periodic. But if psi is irrational, those orbits tend to be dense on the circle. And here are a few illustrations of, so the first two images illustrate periodic orbits. And those are what are called as Birkhoff periodic orbits. And it's a theorem that's actually been proven in convex billiards, that if you have a closed orbit like this and it's periodic, it can traverse in two different ways, and it will still have the same periodicity. The image on the far right is an example of the dense orbits in the circle billiard. All right. Our next example, which is sort of generalization of the circle, is a billiard in an ellipse or elliptical table. And we can also here classify the orbits into three different types. The first one, which is illustrated on the right, is if you have an orbit that passes through a focus, that orbit will always tend to the horizontal line which connects the two foci. But if you have an orbit which passes between one of the foci and the billiard ball, you get the picture on the left, and then it's got these elliptic type, or it traces out another ellipse, which is called a caustic. And the last type of orbit you get in the elliptic billiard is if your initial trajectory passes between the two foci, and you get the image which is on the right. Next on, we move to examples of these dispersing billiards, the ones that were studied by Sinai. And you can see that in these examples, we have flat walls and we have dispersing walls, which would usually be called concave, or what we would understand as concave walls. But the second picture from the right, that is the billiard that Sinai studied in his paper. And he actually put it as a sort of like an image of these squares, and the gray area, that's sort of like the gas molecules, and then you would have a smaller molecule that would traverse between these. And the last picture on the right just illustrates sort of what happens and the chaotic orbit that you obtain. Our next example is what we call a stadium billiard. So it's sort of like the circle billiard, but stretched out. This was introduced by Bonamovich in 1979, and it was the first example of a convex type billiard which had chaotic orbits. Before this, they assumed, they sort of classified and said that dispersing billiards would always have chaotic orbits, and focusing billiards would either be periodic or they would be ergodic in the sense, but still not completely chaotic. The stadium billiard was the first which was shown to be completely chaotic. And I'll also briefly mention just polygonal billiards because they also arise, and this is that would have been an example of a polygonal billiard. And the way that this is studied is they unfold these polygons around their axes. I'm not too well versed of my PhD studies, but you get some good theorems out of it, and some number theoretic stuff comes out of it as well. Right, on to sort of the actual part of my talk or topic. But before we get to the asymmetric part, I first need to give some background. And this is the gravitational wedge billiard, which was introduced by Lettiette and Miller in 1986. And why it's symmetric is you can see that there's that angle theta, which is made between the wedge walls and the vertical. And we also have this particle moving around. There's a gravitational field in which the particle moves. In essence, we are assuming that this wedge is vertical, right? And I also just gave the descriptions of the regions of motion there, and also the wedge walls, which is illustrated by partial Q1 and partial Q2, those boundaries. So what the authors did in studying this billiard is they introduced, or they focused on the variables U bar and W bar, which are the components of the momentum in the radial and transversal direction, respectively. You can show that sort of the dynamics are known between collisions because the particle is going to follow a parabolic path. So the interesting part of this billiard is the collisions itself. And you can derive two collision equations. The first one is where you would have a collision on the same side. So If the particle starts on partial Q1, then it collides with partial Q1 again, which was the right-hand wall in the previous slide. And that's given by the third equation in the center of the slide. And you can also derive collision equations where you have a particle starting on the right-hand side and it collides with the left-hand side. And that's given by the last three equations on the slide. And now that we have these discrete equations, the question is, what's the dynamics? How does the dynamics evolve? And what is very interesting is that irrespective of how you launch this particle, dynamics seem to be determined by the angle between the wedge walls and the vertical. If that angle is greater than 45 degrees, we have completely chaotic dynamics. But if that angle is equal to 45 degrees, then it's the integrable case, and we'll discuss that a bit later. But if the angle is less than 45 degrees, then you get a mixture of periodic and chaotic dynamics. And I'll illustrate that with some phase diagrams a bit later, but let's first talk about, as one does in dynamical systems, fixed points. That's the first thing you ask. Are there any fixed points? And indeed, there are in this case. So for collision on the same side, the fixed points look like what's illustrated on the first line. And essentially what it's telling us is that the only fixed points given by our maps is the particle sliding up or down the wedge wall, right? But for the collision map with the opposite wall, you get the equation which is illustrated in the middle of the slide. And on the right, I've given a graphical representation of this. And it just corresponds to the particle sort of bouncing between the two walls with the same trajectory without any changes to it. But this fixed point is stable whenever the angle is between 0 and 45 degrees. But it is unstable between 45 degrees and 90. So any small perturbation would lead to completely chaotic dynamics for theta between 45 degrees and 90 degrees. So Lettiert and Miller in their paper also gave these equations for more periodic points. I will admit I did not derive these during my PhD. I took their word for it, but I'm pretty sure that it will work out. Well, I'll illustrate a bit later something which I want to say tends to confirm these periodic equations. Right, this is the phase portrait which they introduced in their article, and which sort of gives us an idea of the dynamics in the wedge billiard. The parabola given there by gamma 0 corresponds to pre-images of starting points which would collide with the wedge vertex. And this is the only time where we will assume that the particle stops its motion is when it collides with the wedge vertex. Otherwise, this particle will move on into infinity or infinite times. The line given by gamma 1 corresponds to collisions with the wedge vertex for particles starting on the right-hand side of the wedge. And that line gamma 1 divides the phase space into two regions, which is B and A. A will contain collisions with the same side, whereas B contains collisions with the opposite side. And that little cross in the center of the figure, that is the fixed point trajectory for T of B. So for the map of opposite side collisions. And this is an illustration of some of the dynamics. So the left-hand picture is what we get when theta is equal to 45, and that's the integrable case, like I said. It's sort of, you can get nice solutions, and you can talk about exact solutions in this case. Whereas for theta is equal to 43 degrees, which is the center figure. This illustrates what I mentioned about the mixture of chaotic and periodic behavior. The periodic behavior is illustrated by the ellipses in the face, whereas the chaotic behavior, which is also illustrated by the figure on the right-hand side for theta equal to 60, that corresponds to random dots in the phase space, right? So you can see for the case where theta is equal to 43 degrees, we have this mixture of closed curves, which illustrate periodic behavior, but also random dots, which fill up sort of the rest of the phase space. What was also interesting in a later paper, which I'll reference further study, is that for theta equal to this ratio of pi over 210, you get minimal chaotic behavior. And I've plotted this for different values of n. I did n equal to 2, 3, 4, and 5. And you can see that for the rightmost figure, we predominantly have closed curves, which corresponds to periodic behavior. But you can see on the outside of the parabola, there's sort of this, there's a lot of random dots and stuff, which corresponds to, which tells me that there are initial conditions which will lead to some type of chaotic behavior. What is also interesting in the wedge billiard is that there are cases where you get bifurcations, where the dynamics sort of change. And the first one is at theta's approximately equal to 34.265 degrees. You can see as we, in the phase portraits, as we go from left to right in the phase portraits, you can see that the dynamics show this bifurcation by going from an upright triangle to like a six-sided star, if I can call it that, to down pointing triangle. Next picture illustrates it a bit more clearly, but this is now for a wedge angle of approximately 25.9 degrees. And again, going from left to right, you can see that we go from this mixture of periodic and chaotic behavior, but it's mostly chaotic. Then we get this, the middle figure is sort of at that angle, and then the right-hand figure is slightly below it. And you can see that this implies that there is some change in the dynamics because there is some change in the amount of periodic orbits that is being illustrated in the phase space. Richter and his co-authors gave a more general formula, or they were able to derive a more general formula for where these bifurcations should occur. And I've verified the formula against these two angles. Coincidentally, these two angles that I gave in this slide and the previous slide was derived in the original paper by Lettihet and Miller in 1986. Right. So with that background, we now turn our attention to the asymmetric wedge billiard. I asked myself the question, how will the dynamics change if the symmetry of this wedge is broken? Symmetry in terms of the wedge angles with the vertical, as I illustrated there on the left. Usually when we remove some desirable property like geometric symmetry, it should change the dynamics. And I would say that maybe the dynamic here become completely chaotic because the symmetry in some respect gives us the nice dynamics that we saw in gravitation and the symmetric case. So this is what I said, okay, let's investigate this further. Interestingly enough, there is very little in the literature about the asymmetric wedge billiard. The two articles I gave only mentioned the asymmetric billiard in one paragraph in the appendix. So this is both a good and a bad thing. It's a good thing because it gives us something to do a PhD about. Well, I wouldn't say it's a bad thing, but maybe another good thing. We don't have anyone to follow. It's completely completely new discovery for us. Again, we follow the same sort of approach as was the case for the symmetric case. We will look at the momentum components, except here we introduce a few extra variables. So for the symmetric case, we had capital X and capital Y. But now for the asymmetric case, we have capital R and capital S as well. And the two bottom equations illustrate the collision equations or the collision maps for collisions with the same side, which I call F of A and G of A. So F of A is a collision on the right-hand side wall. So particle starts on the right-hand side wall and collides with the right-hand side wall. G of A is particle collides with the left-hand side wall if it starts on the left-hand side wall. And you can see that these look similar to what we had for the symmetric case. They're nicely behaved. They look like nice equations in that sense. But once we go to opposite side collisions, it becomes a bit more verbose, if I can call it that way. I introduced two parameters here, alpha 1 and alpha 2, which correspond to the tangent of theta 1, theta 2, respectively. And F is the collision for particles starting on the right-hand side, colliding with the left-hand side, and G of B is particles starting on the left-hand side, colliding with the right-hand side. And I actually did the algebra and checked that if theta 1 is equal to theta 2, this metric, then these equations collapse to what we had for the symmetric case. Again, now we ask, what is the fixed points of these maps? And form as what we had for the symmetric case. The fixed points, again, correspond to this particle moving up, sliding up or down the wall. So it's not, I'm going to say, interesting in that sense. But for those opposite side collisions, F of B and for G of B, we have these very complex and it not do, and I realized it only afterwards, is what happens if I set F of B equal to F of G, whether I could get that single period trajectory which we had for the symmetric case. But my numeric simulations, it seemed that this is not going to be the case. So that single period trajectory only seems to happen in the symmetric case. So we can now say, okay, let's look at, we use the same phase space as we had for the symmetric case, except now what happens, that gamma 1 of F and gamma 1 of G, those lines are now, again, they correspond to initial conditions which will collide with the vertex. And you can see that now we might have some overlap if we have same side collisions. So you won't be able to say whether the same side collision is on the left-hand side or on the right-hand side. And that's where I introduced the sort of these separated phase spaces. And this also sort of gives another intuitive idea that maybe my asymmetric wedge billiard could also be two separate symmetric ones which are coupled. So that's another approach to take to this as well. But doing this, and we'll come back to the phase space and look at a few examples, but simulations illustrated, to my surprise at least, that if the wedge angle theta 1 plus theta 2 is greater than 90 degrees, we have completely chaotic dynamics. If theta 1 plus theta 2 is equal to 90 degrees, and we'll discuss this case in detail a bit later, it's sort of like an orthogonal wedge. The two walls are perpendicular to each other. In this case, the dynamics are also more things. And for theta 1 plus theta 2 being less than 90 degrees, it will be a mixture of periodic and chaotic dynamics. So the first one, this is an illustration of the phase space in the case where the sum of the two angles is equal to 90 degrees. And you can see that similar to this wedge billiard, we have again these lines which tells us that this is integrable dynamics. It's something which is nice and predictable. Here is two illustrations for when the angle is less than 90, sum of the angles, sorry, is less than 90 degrees. And again, you can see this mixture of sort of random and chaotic dynamics, chaotic and periodic dynamics. What is nice is you can see on the rightmost sketch, on the left face portrait, that there we have a lot of same-side collisions, which sort of makes sense because your left-hand wall is going to be very flat. So it sort of illustrates the dynamics we expect. Some more examples where the dynamics were very nicely behaved. And the angle phi in these images are just the sort of the initial launch angle I chose for the particle. Now, studying the asymmetric case, we can talk about specific special cases. The first one is where we say, okay, we choose theta 1 and theta 2 in such a way that essentially we're taking the symmetric wedge and we're rotating it away from the horizontal. And that's illustrated in the top line. Omega is sort of the total wedge angle, if I can call it that way, between the two wedge balls. And phi in this equation, yes, that is the rotation angle. And that's illustrated in the sketch itself. So if phi is very small, the dynamics are very close to the symmetric case. But if phi increases, what you see in the phase portraits is you sort of see squashing of the phase portrait in one, say on the left-hand phase portrait, and stretching in the other one. So, and that just illustrates this sort of like this idea of the rotation offsetting our phase portraits. It was interesting to see in the simulations. Another thing which was interesting is that first bifurcation angle I had for the symmetric wedge is still there, but it's offset by 5/4. I couldn't pick up a relationship between the rotation angle and the change in the bifurcation angle. That's something for future research, further investigation. But now we get to the second special case, which is, as I said, where theta 1 plus theta 2 are equal to 90 degrees, which gives us integrable dynamics. And in this sense, we can sort of think of theta 1 also as a rotation angle. So it sort of tells us how far this wedge has been rotated away from the vertical axis. The collision equations, those horrible things I had earlier, actually become something very nice and gives us something that we can work with. And I've illustrated it here. The top two are collisions on the same side, so left-hand side and then right-hand side, F of A and G of A. And then the last two are collisions on the opposite side, given F of B going from left to right, and G of B goes from right to left. But for this special case, we can introduce another set of coordinates, which is given by the tildes, which is illustrated by the red coordinate axes in the figure on the left. And what you find is if you work in this tilde coordinate axis, the Hamiltonian, which describes the motion of the particle, decouples into two one-dimensional Hamiltonians. And this sort of corresponds to thinking of the particle moving either very close to that axis E tilde of x, or the particle moving very close to the axis E tilde of y. And in this decoupling, and in the limit of the particle being close to one wall or to the other wall, you get these trajectory bounds, which I've written in the last two inequalities at the bottom. And it's actually nicely illustrated if we look at, these are physical trajectories. You can see that the bounds sort of are illustrated at the top. It gives this nice rectangular area in the physical space in which the trajectory is restricted in its motion. And what's also illustrated in the first two trajectories is sort of the density of the orbit. So it comes back to this idea of what I discussed with the circular billiard, where if a certain condition is met, then we hope there's going to be periodic orbits. But if not, then the orbits are going to be dense. And as you can see in these three images, the first two show completely dense orbits in terms of the collisions as well. But the figure on the right-hand side of the slide sort of hints towards a possibility of periodic orbits in this special case. And to get towards that, we look at the fixed points of these maps for this special case. And again, for collisions on the same side, the fixed points just correspond to the particle sliding up or down the wedge. But for collisions on the opposite side, we could derive these fixed points equations, which I've written here. Sorry. And ironically enough, these two are sort of related to each other. You can plug one into the other and you sort of get the same thing. So there's I want to say like a symmetry in these equations. For the fixed point orbits, for the symmetric case, where the rotation angle is now 45 degrees, but the wedge angles are perpendicular to each other, you can actually show that you'll get the period, I call it the period 1 trajectory, which is on the left, but you get also this period 2 trajectory, which is on the right. And for the symmetric case, which this is illustrating, those are the only periodic orbits you get. If you take the fixed point maps and you plug them into the dynamic maps, it actually higher periodic orbits. If you try to do it for higher periodic orbits, it just comes back to the period 2 one. So the periodic orbits in the symmetric case. But I found this result here actually first versus a mistake, but the mistake put me on the right path. If we have the rotation angle as given by the first equation on the slide, where P and Q are integers of choosing, and you plug those into the fixed point equations and into as initial conditions for this billiard particle, starting on the right-hand side wall, then what you obtain is a periodic orbit with period P plus Q. And it will have P collisions on the right-hand side and Q collisions on the left. And the argument is actually very similar to what we would do for the dynamics in the circular billiard, but it relies on this reference system, the tilde reference system I introduced. And considering these limit cases of the particle being close to the right-hand side wall or close to the left-hand side wall. Right? The details of actually why this works and how it works is in a manuscript. I've given the link to the archive article, but I've submitted this for publication. It's currently under review. I'm still waiting to hear back from the reviewers and the editors. But to illustrate these periodic orbits, I've given two of these orbits. So here I've chosen P and Q, P equal to 3 and Q equal to 1 on the left-hand side. And as you can see, we have 3 collisions, right-hand side, 3 collisions on the right-hand side, 1 collision on the left, and the total period is 4. It starts repeating. Image on the right-hand side, I've chosen P is equal to 2 and Q is equal to 5. And you actually have 2 collisions on the right-hand side and 5 collisions on the left. But these periodic orbits, I wasn't able to prove this, but only prove it via simulations. These periodic orbits are unstable. So if I make a small perturbation, then it goes back to densely filling up that square, which is given by the energy bounds. And then I also went and plotted this out of interest sake. This gives us the wedge angle, not the wedge angle, the rotation angle theta compared to the radial component of the particle. And what is interesting is that you would see, it's not illustrated there, but on the right-hand side of the slide, rightmost side, that should be theta equal to 45 degrees, where we have the symmetric edge. And there should be a singular dot over there, but I couldn't get it plotted in this. But what is interesting about this figure, which I'm still trying to analyze and get to it, is it sort of illustrates the periodic collisions, which I've illustrated here. And you can also see, similar to the logistic map, if you do the bifurcation map of the logistic map, you can recall that there's the period doubling bifurcations and the window of chaos window in between. And it also seems that there are these certain windows, which I assume corresponds to our periodic orbits. I've just not been able to show that there's any relationship between these windows, like Feigenbaum's constant. So this is it's a very nice picture, but I still don't completely understand what it means and what I'm trying and what we can infer about the dynamics. Coincidentally, it's symmetric, so which corresponds to symmetry. So if we go from 45 degrees to 90 degrees, then this image would just sort of be, it would be flipped around the axis to the right and then sort of reflected around. So yeah, that's why I only plotted this way, because of the symmetry. If anyone is inspired by this and might have some ideas, I'm all open to suggestions. But this, I believe, is a very strong result, these periodic orbits. I don't think anyone expected them to exist outside of those 2 periodic orbits that I illustrated for the symmetric case. So I'm quite happy that I was able to get this result and prove that it holds. So as long as you have that your theta, your wedge angle in terms of arctan of P and Q, that ratio, and P and Q are integers. Of course, Q can't be 0. Then, and with your initial conditions for the particles, momentum being related to this, then you obtain periodic orbits. I think that's, for me personally, that is the strongest result out of all the analysis I did. Right. So for future work, I want to say what I didn't do with the asymmetric wedge billiard was analyze the stability of the fixed points. For the symmetric case, it was shown, I probably didn't mention this earlier, but it was shown that fixed point for the particle, the period 1 fixed point, is unstable. Sorry, I did mention it. It's stable for 0 to 45 degrees, but it's unstable. I don't know about the stability of the fixed points for the asymmetric case, because as you saw, the fixed point map or fixed point values were very complex. So that's something we can do. Another thing that remains to be done is probably deeper analysis into bifurcation angles. And also, like I illustrated, once we start rotating the symmetric wedge billiard, those bifurcation angles shift, and to find out if there is some relationship between the rotation angle and the shift in bifurcation. Another thing what we can consider, and this has been done for the symmetric case, is to look at the dynamics with time-dependent boundaries, meaning we could have the wedge moving to one side or vibrating. The vibrating case has been done. There's an article about it, and I think it's been done in theory. So they were able to show that you can get a periodic orbit for a certain frequency of vibration and so on and so forth. But of course, the question is, would this also be true for the asymmetric wedge? But I suspect it will be very complex. I'm currently, this is now part of my sabbatical leave, going to investigate this for the orthogonal wedge because it's so nicely, it's a bit nicer to see if we take the this rotated orthogonal wedge and move it, vibrate it, what dynamics do we get? The other thing we can do, which is it's going to be a lot more complicated, is actually having your wedge angles being time dependent. So having the wedge walls sort of move with respect to the vertical as time goes on. That has been suggested for one application where you have a robotic hand, right, planar juggler. And the last thing, and this has been done for the symmetric cases, is quantum versions. So for the symmetric wedge quantum versions, we have a quantum particle. This has been studied. Don't think of the asymmetric case. So that's also future work. That brings me to the end of the talk, and I'd like to thank the audience for listening. Also the participation. If we go to the Center of Excellence, with the opportunity to present the talk, my PhD supervisor suggesting it, and also the University of Johannesburg for the research opportunity and the financial support they provided to me during my PhD